So some general announcements to start with, I suppose. There was a prep assignment before class. I hope everybody did it. As usual, the one for Thursday's class is posted already. And then homework, of course, due this afternoon. It was pointed out that I'd left off when I copied the circuit. I left off the source for problem 4. I posted that as an announcement today. But they are all of them circuits we have seen previously, so everything should be essentially the same in terms of sources. So you've done a bunch of impedance calculations already, calculated voltage. So you have essentially kind of done some of the heavy lifting or much of the heavy lifting already. We'll revisit that a bit today. And just close some things up and have some other discussions about power and do more on power. What else? So we'll have homework on Friday, I suppose, and then lab tomorrow. The lab 4B is posted as well, so you can see that. We'll continue with RLC circuits. Yeah.
Yeah, the one
They're in my office. So I have, I noticed that we apparently have run out of caps. There was a whole box of caps. If you took it, please return it. We had a bunch of caps that were sitting out in their own little container, and I don't know what happened to it. I mean, I don't know that anybody in this class took it. I'm just saying, throwing that out there. If you happen to put it in your backpack by accident, it would be nice to get it back. A big box of capacitors is really not going to do you any good. It's not real, it doesn't have any resale value on eBay or anything like that. If you're looking at, I suppose, sell electrical components. With that said, I have ordered more 1 microfarad. Those won't be here by tomorrow, of course. That order just went in yesterday, but I have some tomorrow, so we will have that, I guess, quasi-problematic situation of limited number of components for the labs tomorrow. And someone still has 1 of my inductors, so I have 8, and I started lab last week with 9. Who has an inductor? Was it you guys? No. Miss Chattery, you have 1 of my inductors, did you? No, someone borrowed 1, and I didn't write it down, but I would like to get them back again. They're a little expensive and really don't do you any good. But if you really want to get into the speaker filter design, we can have a conversation about that and how to not use inductors. Inductors are not the best choice there. So that said, we will manage to move forward. We'll muddle through somehow. We may have inductors by tomorrow. That order went in last week, so depends on how fast DigiKey or Mauser is sending stuff out. I guess item of interest to you personally is we have a big holiday weekend this weekend. So Monday and Tuesday next week, we don't have class. If you didn't know that, certainly make a note. When I put together the schedule, I put together a task for next Wednesday, and I didn't think about the fact that it was a holiday weekend, even though I was staring straight at the schedule. I don't usually like to have tasks after holiday weekends. It's just kind of a courtesy to the students. I mean, not that I won't give you work to do over the weekend. I mean, it's not something I'm capable of doing. But I'm not a huge fan of having tasks like right after Thanksgiving or the day after a weekend. So I will throw this out there. I would like to move the exam to the following week. Usually students don't usually mind that too much, but I wonder if anybody has any serious objections. So we would have our exam on the 18th instead of the 11th. So anybody kind of not like that, we'll put that out there. All right. So we will wrap up our material on Thursday. Today we'll spend a bit of time talking about power, and then on Thursday we'll talk about transformers, and that material will be on the exam as well. So, which I probably should have moved that exam date to begin with if I'd been paying attention to the calendar. Other calendar things that matter, I know we talked about this last week, and I'm gonna stress this because I think this is the most important part of why you are here in the engineering program, is getting jobs. So the career fair thing is tomorrow. If it was during my lab, I would say go ahead and miss lab to go to the career fair. It doesn't technically overlap, though vendors may stay a little while, but I give you permission to miss anybody else's class. So if it was my class, I would also say, go to the career fair. This is a big deal. Even if your resume isn't as polished as you would like it to be, better to have a resume, but go to the career fair and talk to the representatives from the various industries. So, it is, I mean, it's why you're here. So it's better than being a lifeguard over the summer, which I did one summer. It's not an engineering pathway to success, even though it's cool to sit on the beach, though the UV rays are bad for you. I have a higher chance of skin cancer, I suppose. So go look for jobs, and I will say this repeatedly even after the career fair, and there are other options to finding work besides industry that I will talk about near the end of the semester as that becomes a little bit more relevant in regard to application. So something else of import, I don't know if anybody noticed on the big screen when you walk in through the atrium there, but there's something called the Bunshaft lecture. That's my pin. Wide. This is Thursday at 7 p.m. So, and it's somewhere over on the podium that you can see on the screen outside. You probably received an email about this at some point. So this is something that's sponsored by our department. Ostensibly, I guess the entire school has been invited because that was part of the morning mail or whatever that's called that you get from UAlbany. But historically, it was largely targeted towards EC department and affiliates. So the gentleman is presenting is, I guess, a student athlete, an astronaut, and a NFL player. So kind of a cool story, I suppose. I don't know anything about him in the past. The speakers have been very good. I will be very curious to what he has to say. I will definitely be going to incentivize, I guess, your interest in going. I did post a link on the announcements where you could register to go. I will offer extra credit. I mean, we all extra credit, not gold star extra credit. Where if you go, I will replace your lowest homework score with a 20. So in other words, that gives you a free homework. If you miss a homework, get a 0. I will replace that with 20. You already have 2 of those already as part of the syllabus. You're allowed to miss 2 homeworks. I don't know if anybody paid attention to that. We said that at the beginning of the class. I dropped the 2 lowest homeworks, but in addition, if you go to the Bunshaft lecture, I will replace one of your homeworks. This may not sound like a big deal, but overall, if you crunch the numbers, it's about 0.5% of your overall grade, maybe 4%, somewhere close to 0.5%, which is a non-trivial amount because 3% is the difference between the modifier, or 3.3, I guess, technically. And so 0.5% can be enough to, if you're near the top of B+, can shift you to A- or C+ to B-, etc., etc. So they will be taking roll. I understand. I checked to make sure that would be taking place. I suppose if that doesn't happen, you can do an honor system type of thing. But if you go, you get 1 free homework assignment. And even if you do all the homework assignments, like some of you are likely to do, whatever your lowest one, I will replace with a 20. But again, it gives you a free one as well. So essentially, you have 3 free homework assignments if you go to the Bunshaft lecture. If you don't go, you get 2. All right. Any questions on the theme? No questions at all? I should make one comment about the task. I suppose something I should have brought up last week when we got the scores back. You can request regrades on the task. So check. I mean, I graded the task to feel like I was a reasonably accurate grader, but it does not mean I did not say too many double negatives. I may have missed something when I graded your test. It happens. Students have pointed out, like, I entered this, here it is, you missed it, or some other related thing. So look through your test, make sure you got the credit you deserve, including partial credit. So one thing that I'm not acceptance of is I think I deserve more points on this. That's not an argument that you can post. You need to say, like, I did this was part of the process, and why didn't I get credit for writing this down? Or if you look at the rubric and it says, you blah blah blah, you missed something, and then if I graded too fast, which sometimes happens, you can say, no, it's right here, look over on this part of the problem, and there's my work, and you missed it. So two arguments that are not valid. One is, I just said, I just think I deserve more points. I put a lot of work in this problem, and that's not it's a valid argument. The other valid argument is, I got 2 out of 8 points, and my friend got 4 out of 8 points, and we did the same thing, and I don't know why I didn't get 4. And I'm like, oh, great, let me know who your friend is, because I would take 2 points off so you get the same score. So my friend got more than me is not a valid argument. But do look, there's a regrade option directly in GradeScope. It's a link somewhere. And you should be looking at your homeworks too to see if they were graded correctly. I realize that's a lot of things to look through, but you know what you did, and you should feel confident, I suppose, in your answers if you got them right and you lost points for them. So all right, so I think that's a fair bit of announcements we had at the start of class. Anybody questions on anything? Life? What's that? Just bored already? Tired? I did not sleep well myself. I overate last night. That was always a mistake, especially as you get older. Don't do that. All right, so I want to just go back and revisit the circuit we were looking at last class. So we'll touch up on this guy again. So some quick writing here. We have F is 159 hertz. And then reminding ourselves that omega, which is what we care about, is 2 pi f. We've seen this number a lot of times 159 is 10 to the 3 radians per second. We always work with radians when we work with impedance in AC steady state problems. I can go through the circuit and say ZR3, of course, is 2K, no surprises there. ZR1 is 1K. Resistors are easy. They're exactly what the resistance value is when we're assigning impedance. Here we have to do a little bit of math and reminding ourselves that capacitor impedance is always negative imaginary. 1 over J is minus J. We can crunch those numbers and we get minus J 1K. And then our source, VS, maybe a little hard to read, zoom in there. There's where we see the 159 hertz. We also see an amplitude of 10 volts. And by default, typically our source reference phase is 0, 10 angle 0 degrees. So no shockers there. I can go redraw my circuit. In impedances, so ZR3, ZR1, ZC, that's 2K. That's 1K and minus J 1K or 1000. The same thing. For some reason, I don't like putting Ks when I have Js. 10 angle 0. And we can approach this a few different ways. We can do some current calculations. So I can look and do circuit reduction. And I can recognize that my Z equivalent is ZR3 plus ZR1 in parallel with ZC. Right, everybody I hope agrees on that. That's something we should be able to look at quickly by this point and recognize that. And so we can do the math out, 2000 plus 10 to the 3 in parallel with minus j 10 to the 3. And ultimately that's 2500 minus j 500. And that's ohms. So our equivalent resistance there, 2500 minus j 500. So there's a bunch of ways to do this problem when we're talking about power. This is one possible approach. So ultimately I can redraw that circuit once again as 10 angle 0 and a Z equivalent of 2500 minus j 500. And so we can look at this again a couple different ways. I can find current if I'm so inclined, and my current, I suppose, to give us a direction, a phase. There's my source current, and IS, put a little squiggly line for phasor, 10 angle 0 over 2500 minus j 500. I'm mixing and matching phasor form and rectangular form. So if I'm going to do this by calculator, I need to convert from one to the other. This seems to be changing. Ultimately, I can go convert this. I'm going to skip some steps here. 0.00392 angle minus 1.3 degrees. So there's my current going through my source. Now all this was set off with a discussion about power. How can I find power? Yeah.
I had a question all the way back to when we
Yeah.
did the parallel.
Right.
I don't know how to do the work for the combining the
This?
parallel with J. Yeah. Like what's the work for that done? Because
So this
I tried
guy?
my homework and I couldn't figure out how to do it. Yeah.
I mean, I literally in MATLAB, what I would do. So this is what I do in MATLAB. But I can show you another way, I suppose. In MATLAB, I type just 1 over 10 to the 3 plus 1 over, and I usually use parentheses, minus j 10 to the 3, or 10 to the 3i to the minus 1. So in MATLAB, the way I would actually write that is 1 over 10 to the 3 plus 1 over, and again, I include parentheses just for completeness. So that's literally what I type in MATLAB. On your calculator, if we're going to do complex numbers, if I have 10 to the 3 minus j 10 to the 3, effectively when I have, you know, Z1 in parallel with Z2, I can write that if you go back and look at some of our earlier work, there is the parallel relationship. So that is effectively one over Z1 plus 1 over Z2. You can find the common denominator, do what the algebra is called, but I guess find the common denominator, gather the terms, and then invert it. And we get what I just wrote a second ago. We get this. That said, this winds up being 10 to the 3, j 10 to the 3 over 10 to the 3 minus j 10 to 3. And then you can convert this. So ultimately, if you were to crunch some numbers, this is something we can write in phasor form fairly quickly. What's the angle of 10 to the 3? Everybody knows this. 0. It's positive real. What's the angle of minus j 10 to the 3? Minus 90 degrees. So we can write these out in phasor form, and then we can do rectangular to phasor conversion here. We get 10 to the 3 times square root of 2, angle minus 45 degrees. And so that's now in a more familiar form. We can do gather the magnitudes, 10 to the 3 times 10 to the 3 over 10 to the 3 square root of 2. And then 0 degrees plus minus 90 degrees minus 45 degrees. Does that make sense?
Yeah,
So this is certainly the long way of doing it. But it does give you a good feel for phasor and complex numbers, so it's not bad practice. That said, I mean, if you're comfortable with that, I would go directly to MATLAB, or you can do the same thing in Google.
Would that be the best way to show it on a test? The way.
Well, so so on a test, they usually try to give you kind of reasonable numbers. It turns out this is what I would call a reasonable number. This winds up being 500 minus J 500. So ultimately, I would do, I guess, in terms of setting up for a test, you're right. So homework or a test, you can't use MATLAB or Google. I would set up a script. So if you have an Inspire, I don't know. So which one's that? So TI-84, I know a bunch of students have a bunch of TI-84s, or a bunch of students have TI-84s. I mean, I unfortunately, I don't use a calculator, so I'm not gonna be able to give you any direct guidance, because I always have access to MATLAB. I don't have to take tests. But I would say there's gotta be a YouTube video or how to do complex numbers on your calculator. I mean, did you look it up on YouTube or?
Yeah, at first.
So in some sense, it kind of, I said this early in the semester, and it's a good point to bring up, you know, learn how to use your calculator. I mean, I suppose I should be telling myself to learn how to use my calculator, even though mine are out of batteries. Again, it's not something I have to worry about it too much, but since you're kind of on the other side of the aisle here, that you're going to be using calculators in multiple classes, and what type of calculator do you have? Do you have
a Casio 9750 G2.
Yeah, I'm not familiar with the Casios, but I mean, as I look at the screen here, I would guess that this probably has complex numbers. Just trying to see. Anybody have a Casio that can confirm that? I mean, you certainly, if you're really jammed up, stop by my office, we can look together. So I'm happy to help, but I mean, for today's homework, if you're still crunching the numbers, then use Google or MATLAB, and then we can go through the calculator. I mean, I don't want you to waste of time. I mean, this is certainly a more tedious process, but this does bring up a point. I don't really want to see you doing this on the test. I mean, this is number crunching in an annoying way. So ideally on the test, I would rather see you do something equivalent to that in your calculator, where you can crunch the number on your calculator. There will be things about phase and magnitude to verify that you understand this, but I don't want you to do that repeatedly on the task. It's a point I tried to make about the exam one. I don't care how fast you can do things on your calculator. That's not what I'm testing. So I mean, occasionally, of course, we have to punch in numbers, but I don't want something where, all right, step 1, step 2, step 3, step 4 on the calculator. That's not an efficient way of testing your knowledge of circuits. So do learn to do it more quickly on the calculator. When we talked about introducing complex numbers, it was more so you're aware of what phasor means and how we can do math, and how we want to represent it. In the long run, take advantage of the fact that the calculator will crunch this for you. You may have to convert back from phasor to rectangular, and you can even, like, I don't know about your particular calculator or even Inspire, but I'm easily confident many modern calculators will actually run a script, or you type a script in, where if you enter a complex number and run a quick script on it, it'll spit out the magnitude and the phase for you. And learn to do that. I mean, have that as a script on your calculator. So I've written scripts like that in MATLAB. I have lots of things that I use in my other class, where I've written like 15 or so different things to crunch out numbers for me. So, and I'm not against that. You do need to understand this process per se, but I don't want you to waste your time doing it on a test. It's not my goal. So, but it's a good point to bring up. So anyway, go back and look at our circuit there. we have a current through the source, we have voltage through the source. What can we find? We care about power, so we're talking about the most important thing in the world. Specifically, what can we find here? We can find power from the source. Is this produced or consumed? Does the source produce or consume power? And it's an easy question. Yeah, produce. There's only one source. There's only one source, it has to be a power producer. It's the only thing it can be. If we have more than one source, one of them can be a power producer, one of them can be a power consumer. We don't know. They could both be producers. They cannot both be consumers. There must, in our circuit, there always must be one power producer. Otherwise, there's no power. We can't just have power consumers. So how can we find our source? Well, we can look at complex power. Remember, we're talking about complex power. So we're talking about this S equals P plus JQ. So complex power equals real power plus reactive power, always. And ultimately for our source, we can look at S equals 1/2. That 1/2 is in there when we talk about amplitudes, is what we're looking at. V times I conjugate, or equals 1/2 magnitude of V squared over Z equivalent conjugate. Because the impedance seen by the source tells us what the current is. So I'm just done some Ohm's law substitution in there. We've written that out previously. Or I can do 1/2 magnitude of I squared times Z equivalent. And notice that complex conjugate here and here. So it's something we touched on and had a video about. And hopefully you've seen that in other classes. I can write this every which different way. So I can write this 1/2 V, which is 10 angle 0. And there's my 0.00392 angle minus 1.3 degrees complex conjugate. And just to do that process, 10 angle 0, 0.00392 angle plus 11.3 degrees. That's the complex conjugate. We talked about that. Just changing the sign of our phase term when we're in phasor form, or if we're in rectangular form, changing the sign of the imaginary term. Those are the same thing. Then ultimately, if I crunch those numbers out, I get 0.0192 minus J 0.0038. And so there is our source. Going way back, we started to do this a little bit. So to kind of pick up where we left off, we have 19.2 milliwatts of real power and minus 3.8 millivar. I'm gonna actually get rid of those watts. Just put M's there. And I got rid of the watts because my units are at the top. So reminding ourselves that real power is watts. Kind of went through the units last class. And reactive power is vars. Effectively, they're the same base units. We just have different labels to differentiate the type of power they are. Reactive power is imaginary power. Real power is real power. The thing that's useful. And in some sense, we can. Oh, I have a mistake here. I must have crunched some numbers poorly last class. Or written something down wrong. It's unfortunate. So I did say that power tables like this are accounting for engineers, so we can actually fill in our missing tables. Power produced must be equal to power consumed. And the source is the only consumer. I have a kind of a dark line here indicating that the top three rows must sum to the bottom row. And so we can very quickly, we can crunch some numbers to do this as well. But that's 3.8 milliwatts as well, because 15.4 plus 3.8 equals 19.2 milliwatts. And then on the other side, on the Q side, this is minus 3.8. Also mil, because these three rows have to sum to power consumed. So there's our power. And again, if you've done the homework, you've already kind of made this progress as well. So just revisiting those concepts. There are some other things that we can discuss about on this table that we haven't talked about, namely the fact when we talk about complex power, largely we're talking about the magnitude of complex power. So when I write P plus JQ in that rectangular form, that's not how we actually talk about complex power. We talk about complex power in terms of magnitude. So the magnitude of S, this is something we've written down before. The magnitude of S is the square root of the squares. P squared plus Q squared to the 1/2. And this is total power. And we see the units up there, maybe a little hard to see, but in volt amps. And as I said last week, that's what we pay for. We look at the magnitude of our complex power, and that's how much power is produced. So in discussions in power systems, we would say that's a 100 kVA machine. So 100 K, K being 1,000, so 100,000 volt amps. So that's actually not a lot of power to be produced. So, if we look at modern power producers, we're in the meg range, and they typically say megawatts, but it's a little bit of a lie. It's megavolt amps. You have any water? So when I look at this next column, these are easy magnitudes to compute. 15.4 squared plus 0 squared, square root is what? This one we can do without a calculator. That's 15.4 mil. Everyone agree with that? 3.8 squared plus 0 squared, square root is 3.8 mil. 0 squared plus minus 3.8, the minus doesn't mean anything. When we square it, it goes away. That's what I mean. It's also 3.8. These are not meaningful numbers. We don't really care about those per se. I have included them for completeness in the table. And then our final thing is not a summation. If I do 19.2 squared plus minus 3.8 squared, square root, I get 19.6, which is not 15.4 plus 3.8 plus 3.8. I want to make this emphasis because I have frequently seen students try to sum up this column. This is not an accounting column. This, however, is an item of interest in terms of being the power provider. So I know that if I'm National Grid or whatever, and I'm delivering power to this circuit builder, they need 19.6 volt amps, millivolt amps of power. And of course, that's a trivial amount of power, but that's what you need for this circuit. I mean, stupid circuit that it is. That's what I would care about. Now, this last term is something we should talk about. So go back here for a second. We have a power factor. EF, shortened to. Power factor is effectively a measure or metric of how efficient your system is. And it's defined as power factor equals the real power, which is always positive, over the magnitude of the total power. That is a boxable equation. That's the definition of the power factor. What do we want our reactive power to be? We want reactive power to be 0. What is the ideal power factor then? 1, exactly. So if reactive power is 0, then the magnitude of the complex power equals the real power. That is the goal. In practice, the power factor is some value between 0 and 1. This is ideal. And this is going to color some of our work today. If you did the prep assignment, you got a quick video about that. That said, I can go back to my little table here. And again, a lot of things are fairly meaningless. But I can look at my rows for the resistor. What's the power factor for resistor R3? If I want to look at that just by itself. What is the power factor for a resistor? Embedded right there. You just answered this question. What's the power factor for my resistor? 15.4 milliwatts of real power, 15.4 millivolt amps of complex power. What's my power factor? 1. So resistors always have a power factor of 1 because the power in a resistor is purely real. So that's 1. It's not terribly interesting for us, but we can include that. What's the power factor for my capacitor? This is a more meaningful statement. They're both meaningful. 0. Because what's my real power? It's 0. 0 over something is always 0. So inductors and capacitors, always looking at them by themselves, have a power factor of 0. That tells us what the device is. If the power factor is 1, whatever it is, it looks purely real. If the power factor is 0, we don't necessarily know what it is in terms of exact component. I just know it's either an inductor or a capacitor, or looks like an inductor or a capacitor. I should qualify that a little bit. Looks like it's an inductor or a capacitor. And that is kind of a more general statement, is what does it look like? Here I can do the math once again. I have 19.2 over 19.6, and here I have 0.979 if I do that out. That brings up kind of an important comment about power factor, because this comes up in a lot of settings. So one of the things the electronic students, the class that comes after, is doing is they're doing or have done AC to DC conversion. Where do we see AC to DC conversion? Every one of you does it every day, multiple times. Where do we see AC to DC conversion? Rectifiers. So you even know what the device is called. So a rectifier is a device that converts AC power to DC power. Your wall outlet is AC power. It is a sinusoidal source. Your computer needs DC power. Your phone needs DC power. Probably many of your other electronics devices need DC power as well. So when I plug in my brick to the wall and then plug in the other side to the computer, inside is a rectifier, AC to DC conversion. Now AC to DC conversion doesn't look like this table. But if I'm designing a rectifier and working for, I don't know, Hewlett Packard or whatever, or whoever does that electronics nowadays, the question I would be asked is, how efficient is your rectifier? And what they would say another way is, what's the power factor associated with your device? So what's your power produced? What relative to your power consumed? And it needs to be hot. This is a huge issue in renewables. So in order to make renewables competitive with natural gas, with coal, all that stuff, this was probably the work was being done before you were born, but they needed high power factors. So the wind turbines are variable speed devices. And so as part of that, to convert it to something that ultimately gets to you, we do AC to DC conversion, DC to AC conversion. Each one of those is its own circuit and has its own power factor. And then AC to DC conversion back to something that's useful for you. 3 circuits on the path from a wind turbine to your device. Actually, there's more circuits, but in a nutshell, 3 circuits. Every one of them has to have a power factor in the high 9s. Otherwise, they would not be competitive devices. So this is a reasonable power factor. If I have a power factor below 6 or 0.6 or 0.9, even power electronics, I will be asked to go work at McDonald's having lost my job. So it is something that we care about a lot in terms of efficiency and electrical design, which kind of brings us up to our next little circuit. Any questions? No questions? Oops. When you look at this circuit, what do you think of? How would you describe this circuit to your parents? Using an electrical engineering term, circuits term. Yeah.
RLC, parallel circuit.
Well, we don't know that it's C. It is parallel though, so that's where I wanted to go. So the Z unknown could be a capacitor, and we'll talk about this a little bit. Also could be an inductor or something else. So we'll get back to that in a second. But more significantly, this is a parallel circuit. So this is actually how your house is wired up. If you have plugs in your house that are wired to the same breaker, they are parallel connections. I suppose we've probably all done this at some point in our lives where we plug things into our strip, and all of a sudden, pop, the breaker goes out. Everybody experience that? So you've drawn too much current. So as we add more devices in parallel, what happens to the effective impedance? Here's a concept question from exam 1. More devices in parallel, impedance goes up or down? Goes down. Impedance goes down, what happens to current? It goes up. Current goes up, what can happen to our breaker? We exceed the rated current for our breaker, the breaker trips. And so go home and do this. Plug lots of devices into an outlet. Get one of those extenders and just keep plugging things in until everything just turns off. It's actually not unsafe, really, as long as the breaker trips or something else bad happens. But you can go check your breaker unit. If you've never checked your breaker unit, go look at it. It's a bunch of things in parallel. Servicing different parts of your house. This is not a completely atypical layout for your house. It's a simplistic setting. So I have 3 components here. We'll leave Z unknown alone for a minute. I should have asked you to write these things down, but what would our heater be in your house? Self-explanatory. Where do you see something like this in your house? Yeah.
Like a space heater?
Could be a space heater. It's a big resistor. The example that I tend to use, space heater is a good example. I've used that as well. Another one I tend to use is your electric stove. If you have an electric stove, your burners just are resistors. That's all they are. And right next to that, plugged into the same outlet maybe, is your mixer. What is your mixer? What is a mixer? From a circuit point of view.
Like a blender.
Well, blender, mixer, whatever. I mean, what is it from a circuit point of view, though? Well, yes, and I gave that away here, but why? Why is it in there? What is, I mean, if I didn't have the schematic up here. What do you think? What circuit, device? This is not something we've necessarily talked about, but coil wire around it. Now you're getting a little bit more specific, more general than that. I mean, what is it? If you ripped it apart, what would you see? You don't have to rip it all the way down, just take the first layer off. What's inside? Yes, that's true. It's a motor. A mixer is something that goes around in circles, which is a motor. So the coils, you make motors with coils, of course. So it's a motor. Motors are largely inductive. So historically, if I look at a power network, your house is connected in parallel to your neighbor's house, is connected in parallel to your neighbor's house, et cetera, et cetera. It's all parallel network. And your house typically looked like two different circuit components. It looked like a resistor, or it looked like an inductor, or some combination thereof. This is an ideal setting. Motors are not purely inductive. So it says L motor there. So that was the giveaway, I suppose. But this is historically what power networks look like. Things have changed, and I meant to look this up before class. We are seeing a lot more capacitance in our power network. I think largely because of storage systems that are emerging. So one of the things people keep talking about, I don't know how this would ever become practically true, but using electric batteries in cars as storage when we produce an abundance of battery, and then using your car to power your house during the night. This is a real thing people have been talking about for 20 years. And I've seen faculty candidate presentations on it. I've seen research posters on it. So it's something people care about. The hard part is getting everybody in the power industry to agree to do this, which is nearly impossible, as far as I can tell. But I would tend to think, I don't know this for sure, that batteries look somewhat capacitive. So we are seeing more capacitance on the network. And so that's a new emergence. But that brings up something we'll talk about as well. I look at this and my source, 60 hertz source, that's a real source, that's our wall power. And in the problem that was on the previous page, I do have a VS equaling 1,000 volts RMS. That is something we want to talk about a little bit, because it affects the way we look at power. So volts RMS, root mean squared, we talked about that last class. I gave you the formula. To revisit that for a second, VRMS equals 1 over square root of 2 V naught. RMS voltage amplitude. When we write our sine wave, we write it in terms of amplitude. Ultimately, if I'm dealing with electronics, power electronics, frequently all I care about is the RMS voltage. If I went in the cabinets and got out some multimeters, one of the settings I can set those multimeters on is to measure RMS voltage. So that's an option. The way this plays out for us a little bit is when I look at complex power, I can say that's 1/2 V naught I naught. These are amplitudes. Which I can rewrite if I want, equals, using Ohm's law, equals 1/2 magnitude of V squared over magnitude of Z equals 1/2 magnitude of I squared. Oops. Times magnitude of Z. So those are the same power expressions we've written down previously, but if I'm just looking at the magnitude of the complex power, P squared plus Q squared square root, I can take this shortcut. And I just need to know the amplitude. And so effectively I can go and rewrite these two as 1/2 V naught squared, because that's just an amplitude over magnitude of Z, equals 1/2 I naught squared times magnitude of Z, because that's already a known value. Magnitude of V is the amplitude. I can also write this as 1 over square root of 2 V naught times 1 over square root of 2 I naught. I just factored out my 1/2 into 2, 1 over square root of 2, 1 over square root of 2 times 1 over square root of 2 is 1/2. But I can look at this expression, and that's the definition for VRMS. Or I could follow this through and I could write this as VRMS squared over magnitude of Z, or IRMS squared times magnitude of Z. And again, RMS is often what we're looking at, or the information we're given when we talk about power electronics. I use both in the homework, so I just want you to be aware. The fundamental difference, of course, is the 1/2. We look, if we're given amplitudes, then we have that 1/2 term in our power electronics term. For magnitude of complex power, let's remember what we're talking about, magnitude of complex power. If we're given VRMS, IRMS, we can only find magnitude of complex power. If we know amplitude and we know Z, we can find both the P and the Q. I suppose if we know Z, we can find the P and the Q no matter what. But when we're talking about magnitude of complex power, we can write this either as RMS expression or as amplitude expression, the fundamental difference being the 1/2. So just pay attention. Everybody all right? So this was given to us a little bit more information. Let's go back. I'm going to grab my table here. I'm going to paste this twice. So going back to our problem, this definition, I also was told the magnitude of real power is 20 kVA, 20,000 volt amps, with a power factor of 0.6. I just got fired. This is a terrible power factor. 0.6. So I can go to my table now, and there's 2 things I can write down right away. In both these tables, they're the same. I can write my power factor, and where I have to be specific, it's associated with the source. 0.6, 0.6. That's 20K, and that's 20K. There's my source. I know the magnitude of complex power produced. So I'm paying for 20 kVA units of power, whatever that cost me. And I'm wasting a tremendous amount of that. Given that as a power factor, what can I find? Or given that as a magnitude of complex power and a power factor, what can I find? What can I find? Ignore the other rows, just working on this row. I can find the source real power. I can find the P associated with the source. Because I can go to the next page here and write P source. Well, let's rewrite it for a second. Power factor of the source, which we were given, equals P source over magnitude of S source. Well, we know this, 0.6 equals P source over 20,000. And if I crunch that out, I get 12 kilowatts. And that's again true for both. 12 kilowatts, 12K. That's the only part of my power that's being useful. I'm wasting a bunch of other power that's contributing to reactive power. I can ask the question, how do we find the Q for source? And you know how to do this. You can't. So remember, complex power is P squared plus Q squared. So they are not additive relationships. So when I look, complex total power, magnitude of S is P squared plus Q squared to the 1/2. Or I could rewrite this ultimately as Q squared equals magnitude of S squared minus P squared, just doing a little bit of rewriting, and then I can take my squared there and rewrite this as 1/2. 20,000 squared minus 12,000 squared. And here's the quasi-tricky thing that I left in this problem. I haven't fully written that out. If I have a square root, what are my possibilities? I have two possibilities. Positive or negative. So I didn't specify. I would need to give you more information, and I will give you that context right now. This winds up being plus or minus 16 kVAR, kilovar. Reactive power being those bars. How do I know if it's positive or negative? Well, in this problem, I don't. I didn't give you enough information. But there is context. In a system that appears inductive, I'm not saying it's purely inductive. I'm saying Z equivalent is some Z real plus some J Z imaginary. Remember, positive imaginary is inductive. Impedances that are positive and imaginary are inductive impedance. Plus J omega. Don't usually say it plus J omega. The system that appears inductive, the reactive power will be positive. And I can copy that because I have the beauty of an iPad, I suppose. People still writing? Good? And a system that appears capacitive. We have a minus sign because minus imaginary, negative imaginary, we know is capacitive. And the reactive power in this case will be negative. So in other words, Q greater than 0, inductive overall. Doesn't mean there's no capacitors in it. It just means the inductors are storing more reactive power than the capacitors. Q less than 0, capacitive overall. And these are questions we also ask. In our power system, does our network look inductive? Does our network look capacitive? Historically, they largely looked inductive. But that said, this is why I have two possible answers here. So going back to this, I could say I have plus 16 kVAR Here, I could say minus 16 K var. This, I suppose if I can give myself a little bit more room, is an inductive system. This is a capacitive system. Again, this doesn't mean there's no inductors in this system. It just means it looks capacitive overall. Here doesn't mean there's no capacitors. In this case, there aren't any, but it just means it looks inductive overall. So there's my two possibilities. I left it open, and I want to talk about this a little bit. So going back to our problem definition, we can fill out a little bit more information. We don't have to do any math. What can we say about the Q associated with the resistor? We all know the answer to this. Yeah. Everyone hear that? Q associated with the resistor is 0. What can I say about the P associated with the inductor? You were nodding your head, Mr. Wu. What was it? What's that? You're not thinking. What's the P associated? What's the real power associated with an inductor? Missing 0. It's always 0. So we don't have to do any work. If something is purely real, we can put a 0 in the Q. If something's purely reactive or purely inductive or capacitive, we can put a 0 in the P associated with that device as well. Now, largely, that's not the case. Again, if we're talking about real electronics, it's usually a blend of resistive and reactive components. So my L motor always has a resistive component, and we've been talking about that in one of my other classes as well. So, but here we're keeping things a little bit idealistic. So I can do a little bit more work now. If I know the voltage of my source, then what's the easiest way of finding power? It's a parallel network. I know the voltage across every component of the network, right? That's easy. So we can go find S. I mean, I can write it down. S for R heater, put a little H there. We have VRMS, so I can write 1/2 VRMS squared over ZR heater conjugate, just to write it out in complex form. Oh, not 1/2. I'm being bad. I forgot what I was doing. We're talking about RMS. No, 1/2 is in RMS. Just VRMS squared. And we were given some values here. That's 10 to the 3 squared, or 1 million if you like. And that's 100 conjugate. What's the conjugate of 100? $100. There's no imaginary term. And that's 10 to the 4th. If we want, plus is J0, but we already know this is 0. We already put that in our table. So 10 kilowatts of real power. And that's true for both tables. We can look at SL motor, and that's still VRMS squared over ZL conjugate. And this was given, I wrote 100 there. I should have been a little bit more careful and put J100. It's an inductance. That's an impedance that was given. I didn't give us the actual circuit values. That's an exercise we could pick up, certainly. So there's the same 10 to the 3. It's parallel. We don't have to do any real work there. We know exactly what that is. And that's J100 conjugate. But what's J100 conjugate? Minus J100. And if we do that out, we get 0 plus J 10 to the 4th. Everybody agree? I mean, certainly you can check the phasor math, but I can go to my little table. And this is 10 to the fourth plus, if I want, plus 10 to the fourth. So I have that unknown device in there. What must be true about my columns here for P and Q? Accounting applies. What's P in both tables? They're the same. What's P for my unknown device? What does it have to be? 2K, it has to be 2000. Here, this is different. So if my total power has a positive reactance, 12K plus J 16K, inductive looking, then in this case, I know my unknown device has to have plus 6K. We agree? Do we agree? What does this have to be? If my overall system looks capacitive, I know I have an inductor in there. I have to have a, I guess, bigger, more powerful capacitive branch. So what's my reactive power for the bottom table where my system looks capacitive? What did I say? Accounting still applies. What's that? Negative 26K. So two things I can ask that follow up. What is the unknown here? What is the unknown? So it's arguably a little bit of a little bit more complicated question. What is my Z unknown? What is it? Physically, what is it made of? I mean, I don't care what type of thing it is. Motor, not a motor, whatever. What is it from our circuit parameters point of view? What is it made of? What does this have to be? It's actually two kind of possible answers. But we can qualify them physically the same way. What does it have to be made of? How do I get 2000? Yeah.
Could be a resistor and.
It has to be a resistor and an inductor. To get a real impedance, we must have a resistor in there. And to get a positive imaginary impedance, we must get an inductor. It can be either positive, it can be either in series or in parallel. I'm going to do the series option because it's much easier mathematically. And that's not the correct thing. Let's be very careful here about what I write. That's not Z unknown, that's P unknown. I want to find Z, or I want to find R and L. How do I find, that's an R. How do I find? So I had written that Z there, but that was wrong. That's the power row. Let's emphasize that point. 2K plus J. This is power, P plus JQ. That's the complex power. So, oh, and let's be even more careful. That's S unknown. So, complex power. I'm getting careless here as we end class. How do I find R and L? Well, I need to find Z unknown. But what do I know about the relationship between Z and S? S is the RMS, which has the same voltage over Z unknown conjugate, right? I already have all this math out. I need to do a little rearranging. I can write Z unknown conjugate equals VRMS squared over S. S is a complex number. Let's point that out. We have it up at the top of the page. I can put a little UNK for just to make sure we're reminding ourselves what it is. And I forgot to write this down, so bring that up quickly. But one thing to point out here is I have conjugate here. I can rewrite this. I can take the conjugate of the whole thing. What's the complex conjugate of a complex conjugate? Yeah. It's itself. So complex conjugate minus the imaginary term winds up just being the imaginary term. What's the complex conjugate of a real number? VRMS is a purely real number. Complex conjugate of a real number is a real number, so we don't have to do any work there. So ultimately I can write Z unknown equals VRMS squared over S unknown conjugate. I could do a little bit of math there. That's 10 to the 3. It's still the same voltage. We said that. It's in parallel. Squared over 2000 minus J 6000. Just taking the complex conjugate of what we have at the top of the page. And we can crunch that up. 1E6 minus 6000I minus 1. And we get equals 50 plus J 150. So there's our impedance of the unknown, and now we can do some really quick work there. We can't finish. What's my value for R? 50. It's right there in the problem. Z unknown is VR plus VL. I mean, that's effectively what it is. So this, it's a series circuit equals ZR plus ZL. These guys, of course, the resistor value for impedance resistance is the impedance resistance. So we can go put 50 there. And I didn't do this in the given problem, but I can find out what L is. Because what's ZL? ZL, I leave off my J. Well, ZL is J omega L, which we just found. We have J 150 equals J 2 pi. Way early on, I said we were at wall power, 60 hertz, it's 377 times L. And so if I wanted to, I can again go crunch some numbers really quickly. 150 divided by 377 minus 1, and we get 0.398 henries. And there's my parallel unknown circuit. I could go way back to where we drew this out, and I can now draw a resistor and an inductor in there that look horrible. And I know what's in my unknown circuit by just going kind of backwards from my power expression back to impedance, back to resistor and inductor values. Do we agree? Do we agree? Any questions? I rely on you to ask questions. Anything not sure? That said, what is the problem with this circuit? And we can look at the top one. We could do the same thing on the bottom. What's our Z unknown in the bottom one? What's it going to look like? I'm not going to crunch through the numbers, but we could do it. What's the circuit for our bottom one? A resistor in series with a cap, or a resistor in parallel with a cap if you feel like doing more work. Either one. They're both valid answers. They'll give you different values, but both valid answers. That said, why is this a terrible problem? Terrible design, problematic design. Because complex power, the magnitude of complex power far exceeds the real power in the system. I can add another parallel device. So I can go back, we can work with the one we're looking at. What can I add in parallel that's going to make the system produce real power? It's accounting. So if I go back and look at my table, essentially when I'm looking at a parallel network, it's power of load 1 plus power of load 2 plus power of load 3 plus, if I have more loads, power of load 4, power of load 5. I have many loads in parallel to the power network. All I have to do is add. What can I add to this system to make this go to 0? What can I add to the system to make this go to 0? I can add a capacitor. So I can go back and add a capacitor, and we won't have time to crunch some numbers, but this is what we touched on in the video. I can add a capacitor, and what's the beauty of the capacitor? I can eliminate all that reactive power and take my total magnitude of complex power down to 12K. This is a real thing. This is power compensation. It actually happens in industry. So there are two ways to do power compensation. You can do source side compensation or load side compensation. And which one you do depends on who's the bigger player and who forces it on one or the other. If the load is the consumer, the source is the producer, and they can fight with each other over who's responsible for doing power compensation. It's arguably easier on the load side. But as you pack up, power systems are dynamic. I don't run my mixer all day long. This drops out of the network. Maybe I hook up my TV instead, which could be capacitive. And so what happens? My network is changing. How do we do compensation when the network is changing? We have variable capacitor banks that switch in capacitors on and off. Actually, I can show you a picture of those. These are huge capacitors. With switching circuitry that adds capacitors in and out of the system as compensation is needed, as the network changes in real time. So we want to monitor. It's a big thing now. How do we monitor the power network? All right.